This video presents the work of Aurélien Nioche, Pierre-Alexandre Murena, Carlos de la Torre-Ortiz, and Antti Oulasvirta, entitled Improving Artificial Teachers by Considering How People Learn and Forget. In intelligent tutoring systems, an artificial teacher is in charge of choosing the right teaching materials to present to a learner. As an example, self-regulated teaching applications, such as Duolingo, help the learners learn new vocabulary in a foreign language by choosing words to present to the learner. The learner selects the translation of the word in a list of multiple options and gets the correct answer from the application. In this example, the difficulty of the teacher's task is to choose which word to present at each time step in order to maximize the number of memorized words. If the learner had a perfect memory, the task would be much easier. It would be sufficient to present each word once. In practice, human learners have only imperfect memorization, and it is therefore of primary importance to present each word multiple times. Determining when to present again a word is not trivial and depends on multiple factors. For instance, some words are easier to remember than others. In a similar way, some learners learn quickly, some require more time. This diversity in the memorization behavior reflects the importance of individualization for both learners and learning material. Also, the learner does not have infinite concentration capabilities and requires some breaks in the learning, which needs to be taken into account when teaching. For instance, it would be useless to introduce a completely novel word to a user just before they take a one-day break. Indeed, the learner would not have time to memorize it, and it would have been more useful to revise an already seen word. Based on these reflections, we propose in this paper a novel approach to solve the problem of choosing the learning items to present to a learner. This approach incorporates a model of how the learner forgets, which is individualized for the learner and for the item. This model, the parameters of which are inferred online during the interaction, is then used to plan which items to present based on the learner's practice schedule. By modeling the teaching process as a partially observable Markov decision process, we show that we can describe it as the interaction between three entities: the human learner, an artificial psychologist, and an artificial planner. When the learner gives an answer, be it correct or not, their performance is observed by the psychologist and used to update the parameters of the memory model for this item, as well as their uncertainty. The psychologist then transmits its predicted learning performances to the planner, that is to say, the probability of recalling each item. Based on this information, the planner will consider which item to choose next in order to reach some specified learning goal. During this exploration, the planner considers the learner's practice schedule and exchanges with the psychologist to get updated probabilities of recall after potential interventions. After exploring multiple choices of items, the planner presents to the learner the item that maximizes the expected reward. This interaction process is very general, and we now present a simple implementation we propose in our paper. For the memory model, we consider a simple exponential model. The probability of recalling an item decreases exponentially over time. The decay depends on the number of repetitions of this item. The more the item has been seen by the learner, the slower the probability decreases. This model depends on two parameters: the initial forgetting rate and the effect of repetition. These parameters are inferred by the psychologist based on a Bayesian belief update. The goal of the planner is to maximize the number of items learned at the end of the process. In order to evaluate it, we take as a proxy the number of items having a probability of recall larger than some threshold. The goal of the planner is then to maintain a high probability of recall for as many items as possible. The planning phase itself is extremely costly because of the large number of items and the large horizon. We propose two simple alternative methods to alleviate this. A myopic planner, which operates greedily and gives priority to items being forgotten without consideration for the longer horizon, and a conservative teacher, which guarantees that no presented item will be forgotten at the end of the teaching process. For the empirical evaluation, we compared our implementations to the Leitner system, a rule-based system which is currently an industrial standard. We first tested our methods with simulated learners under similar conditions as human learners. Each agent participates in one session a day for 1 week, followed by an exam. We observe that our methods globally outperform the number of items learned by the Leitner system, be the parameters known in advance or inferred by the psychologist. However, we notice that the myopic planner suggests way more items than what the learner can memorize. The ratio of items learned over items seen is very low, especially compared to the baseline and to the conservative planner. Similar results are observed with real human learners. We observed the performances of 53 users learning Japanese kanjis with a Leitner system and our two implementations. This user study confirmed that the myopic teacher globally outperforms the baseline in terms of items eventually learned, but at the price of presenting way more items, which can be frustrating for a human learner. The conservative teacher, however, presents performances similar to the baseline. This result is encouraging. It shows that it is possible to reach excellent performances with a simplistic memory model and elementary planning methods. It is important to note that, unlike the baseline, our method is extremely modular and can be adapted in many ways. For instance, to assess interaction effects between items, to incorporate user customizable objective function, or to alleviate the effects of irregular learning sessions. In conclusion, our work extends research on model-based approaches for tutoring systems by offering a modular framework that combines the choice of a memory model, the online inference of the model parameters specific to each user and each item, and online planning that takes the learner's time constraints and learning goals into account. The first experimental results show performances at least equal to the industry standard Leitner method, as well as a successful adaptation to the variability of the learner's learning capabilities and of the item's difficulty levels.